Good evening, everyone. Welcome to session 12 of our Essence training series. Today, we have Dr. S.K. Ghosh once again with us, and he will be taking up the fifth lesson in concrete, and he will be going over columns today. So this will be a very important session, and I hope you learn a lot. And I will just transfer the mic to Dr. Ghosh now.
Thank you, Bodhi. Good evening, everybody. As Bodhi said, this is our session 12 and the fifth session on concrete. We will talk about reinforced concrete columns today. There are pre-stressed concrete columns which I did not include in the scope. I am finding more and more that this 2.5 hours, you can do only so much and no more. We will start with what columns are until you go into high seismic applications. Design categories D, E, and F in chapter 21 of ACI 318. There is no formal distinction between a beam and a column. It tends to be somewhat unnecessary to make that distinction until you get into high seismic applications. There is a definition of columns in chapter 2 of ACI 318 where all the definitions are. And it says that a column has a height to minimum plan dimension ratio of no less than 3. If the ratio is less than 3, then the element is called a pedestal, not a column anymore. And pedestals have somewhat relaxed design rules. So in a building, height to minimum plan dimension ratio below 3 is something you will typically not encounter anyway. So columns are defined as members that carry loads primarily by compression. That is probably the key thing. Most columns carry bending moments as well, about one or both axes of the cross-section, which may produce tensile stresses in part of the cross-section. There are actually hardly any columns that are not also subject to bending moments. And when theoretically there is no bending moment, we still consider a minimum eccentricity of the applied axial load, which will give us a minimum bending moment that we design for anyway. Now, even with bending moments, compression forces generally dominate column behavior. That is, again, the key thing that we are talking about, compression-dominated behavior. Basically, all the time. Not necessarily all the time. Okay, there are beam-like columns, low axial load, high bending moment. In any case, we have in mind compression-dominated members when we talk about columns. 3 column configurations are generally in use. Now, the 3, in my opinion, is probably the first 2. The third one is not very common. Anyway, columns reinforced with longitudinal bars and lateral ties. Those are by far the most common. And this term tie, stirrups, hooks, all of that, I think will be anyway. Next week I will do a session or part of a section on non-seismic detailing of concrete, where those terms will be very clearly defined. But generally speaking, most people are familiar with column ties. So that's number one. Number two is columns reinforced with longitudinal bars and continuous spirals. Now, the spirals typically, not necessarily always, but typically are used in circular columns. Circular columns are fairly common in bridges. The bridge piers supporting the bridge deck are quite often circular, but in buildings, circular columns are, I would say, increasingly uncommon. I do not know definitively anyway what the reason is. One of the reasons I speculate is in, again, high seismic applications. The beam to column joint becomes very important, and we have a lot of reinforcement to place in that joint. When the column is circular and the beam is rectangular, the detailing of that joint becomes very complicated indeed. So that may be the reason, I do not know, but circular columns in buildings, other than parking structures, I should say, are relatively uncommon. And if the columns are not circular, the use of spirals is rather uncommon. Okay, the third, composite columns, where structural steel shapes, pipes, or tubing are encased in concrete with or without additional longitudinal bars, and various types of lateral reinforcement. These composite columns, I do not know how common they are. I do not believe they're particularly common. They are, if you want to design them, you need to go to AISC 360, the steel document. That's where these composite columns are properly treated. ACI has some provisions, but I do not believe that they are all that sufficient. And lately, we have deleted composite columns from 318, leaving it for AISC 360 to cover. So reinforced concrete columns typically would be a tied column or a spirally reinforced column. The longitudinal reinforcement in a column helps in resisting axial force. Very definitely, the concrete carries part of the axial force, the reinforcement carries the rest. Helps in resisting bending moment. You know that bending moment causes tension on one face of a member, and tension requires reinforcement. Thirdly, reduces the effect of creep and shrinkage in concrete under sustained compression. Okay, so shrinkage, you know, is the evaporation of water out of the concrete, load-independent phenomenon. Creep is a load-dependent phenomenon. If you keep a compression on a member, the immediate deflection due to the compression load will increase with time, and the time-dependent increase is called creep. Now, the shortening, how should I say, the effect of creep or shrinkage, the effect of shortening of a member because of creep or shrinkage becomes important when the shortening is restrained. If a member wants to shorten and you don't let it shorten, it cracks because it is set in tension. Now, if you have reinforcement, it helps in containing that cracking. and also when a member shortens because of, let us say, creep, the load that was carried by the concrete now transfers to the reinforcement, so that the reinforcement shortens some more. Like in a member, the concrete part cannot shorten any more than the steel part. The deformation has to be equal. And that requires a load transfer from the concrete to the reinforcement, which does take place. So the reinforcement helps in a couple of ways. If it is there, it does help in a couple of ways against the effects of creep and shrinkage. Okay, this is in addition to resisting axial force and resisting bending moment. In columns with large axial load and relatively small bending moment, longitudinal reinforcement is distributed uniformly around the perimeter of the column cross-section, which you know, and that is logical. In columns subject to large bending moments, much of the longitudinal reinforcement is concentrated near the tension and compression phases. This again is pretty much common sense. Okay, if bending is the main thing, then it is like a beam. You put the reinforcement on the tension and compression phases. Bundle bars are used as longitudinal reinforcement in heavily loaded columns with large amounts of reinforcement in order to reduce steel congestion and tie requirements. Bundle bars, 3 bars and or more bundled together, tied together, I would again say that they used to be much more common than they are today. Again, I do not know about Bangladesh, but in any case, bar bundles are allowed. They are provided for in ACI 318, and as it says, when you have a large amount of reinforcement, then bundling some of the bars may relieve the congestion. That is kind of a sideline that I don't want to spend time on. Lateral reinforcement, very, very important roles that lateral reinforcement plays in a column. It, first of all, resists shear. So the lateral reinforcement is also shear reinforcement. So in a beam, the shear reinforcement is vertical. In a column, the shear reinforcement is horizontal. Those are the ties that does other things. One very, very important thing that the lateral reinforcement does is to confine the concrete, particularly if the lateral reinforcement is closely spaced. And in seismic applications, that is an extremely important role. Concrete has to be confined for it to be, if you confine concrete, particularly confine concrete tightly, it gains strength, but that is not the main thing. The gain in strength, while substantial, is not huge, but the concrete now is, I would use the word ductile. It can keep on carrying gravity loads while deforming laterally by quite an amount. It doesn't disintegrate all that easily. It has ductility and toughness, all the properties that we will talk about when we go to seismic applications. So this confining role of lateral reinforcement is extremely important. Then at a very basic level, prevents longitudinal bars from buckling outward under high compression load. So the bars, most of the bars are under compression, and the cover is thin. The bars cannot very well buckle inwards under compression because there is concrete that it would hit. But if the compression is significant, then buckling out of the bars by destroying the thin cover concrete is entirely possible. It does happen. And to prevent that, we have to place lateral reinforcement again at a reasonably close spacing. 6 times the bar diameter or so is needed to prevent buckling. Okay. Something in that neighborhood. Now, again, even at a more basic level, the lateral reinforcement holds the longitudinal bars in place during concrete placement. And that is definitely not unimportant. Okay, you cannot just have the longitudinal steel and not the horizontal steel if you're going to place concrete. So resisting shear, confining the core concrete, meaning the concrete inside the lateral reinforcement, preventing buckling of the compression bars, and holding longitudinal bars in place during concreting. Okay, under general principles and requirements, this is all ACI 318 and BNBC 2020 section numbers in blue for non-pre-stressed members with spiral reinforcement. Spiral reinforcement has to conform to section such and such, or composite members conforming to section such and such. So this is a very basic equation that gives you the maximum axial load that you can carry on a column. Okay? The phi factor for columns is, according to our discussion on the first day, remember strength design, phi is 0.75 for spirally reinforced columns and 0.65 for tight columns. Those values are for all compression controlled sections. Okay? So the phi is 0.75. So phi times P sub n maximum. P sub n, remember, is the nominal axial strength. The definition never changes. Maximum is what is the maximum nominal axial strength. Okay. So the maximum is important because as you apply more and more axial load, more and more bending moment, the axial load capacity changes. So a column does not have one value of P sub n. What the P sub n is depends on how much moment is applied on the column. Okay. So this is the maximum P sub n. The P sub n is 0.85, and I'll explain that. And then it is simply the summation of the forces, how much concrete carries and how much reinforcement carries. Reinforcement part, very simply, is the total area of reinforcement multiplied by the yield strength of the reinforcement. The concrete part is the area of concrete. A sub G is the gross cross-sectional area minus the steel area. Okay. So where there is steel, there is no concrete. And then we assume a uniform compressive stress of 85% of F sub C prime across the column section. So the concrete carries 85% of F sub C prime times concrete area, A sub G minus A sub ST, and the steel carries A sub ST, the steel area multiplied by its yield strength. You add the two together, you have the column axial load, and we multiply that by a phi for reasons that I explained on the first day. And then there is an additional 0.85 that we will discuss in a second. If it is a tight column instead of a spirally reinforced column, then that number of 0.85 changes to 0.8. For spirally reinforced columns, it is 0.85, and for tight columns, it's 0.80. Also, the phi changes from 0.75 to 0.65. So those two things happen as you go from a spirally reinforced to a tight column. The factor of 0.85 or 0.80. So 0.85 for spiral columns and 0.8 for tight columns are applied to reduce the design axial strength of a column. Why do we reduce it? To account for bending moment caused by accidental eccentricities in the axial load that was not considered in the analysis. Also, reduction of concrete strength at sustained high loads. The second factor, I think, is very secondary. I think I did mention on the first day when we were talking about material aspects that the strength of a material or a structural member made of a material, the strength increases the higher the rate of loading. Okay, if the load is applied at a high rate, high speed, then you will measure higher strength than if the load is slowly applied. So under sustained loading, there is you find lower strength compared to what you would find under what is considered to be a normal rate of load application. Okay, but that is not a huge amount. I do not know that that is the reason for 8.5 or 7.5. That's not a big reason. The big reason is this accidental eccentricity. We may think our axial load is concentrically applied, but in reality, there may be a small eccentricity, and we do consider an eccentricity all the time, because not to do so would be unconservative. Prior to 1977 edition of 318, this was accomplished by requiring a minimum eccentricity of 5% of the column cross-section for spirally reinforced compression members, or 10% of the column dimension in the direction of analysis for tight compression members. So it was explicit consideration of accidental eccentricity. Then we went to these reductions of 15% and 10% in consideration of accidental eccentricity. So there is a phi factor, and then there is an accidental eccentricity factor. So this is the load moment interaction diagram. When you see this shape, it is the, well, I'll come to that later. So we are saying that this is the nominal interaction diagram, the P sub n versus N sub n diagram, where as the axial load changes, let us say on a section. This is E eccentricity of 5% or 10% of H. Now, that if the load is applied at an eccentricity that amounts to a moment applied to the column, so instead of being here, we'll be here on the interaction diagram, and the axial load carrying capacity will go down. This is why the 0.85 or 0.80. Design aids, and so we carried this up until 2008, maybe beyond. Design aids and computer programs based on the minimum eccentricity requirements of the 63 and 71 codes are equally applicable. So instead of taking the 0.85 and 0.80 reductions, you are totally, fully allowed to use accidental eccentricities of 5% of column dimension and 10% of column dimension, that is still allowed. You will get the same result or very similar result. Okay, general principles. Okay, members subject to compressive axial load shall be designed for the maximum moment that can accompany the axial load. The factored axial force P sub u at given eccentricity shall not exceed, P sub u is the required strength, shall not exceed that given in section 1036. The maximum factored moment M sub u shall be magnified for slenderness effects in accordance with. So the slenderness part will come later. This particular provision does not tell you a whole lot that we don't know. Basically, P sub u, M sub u shall be within P sub n, M sub n. The thing that you always have to keep in mind is that a column is always designed for combined bending and axial load, as opposed to a beam, which is designed only for bending moments. So there is always a P and an M, combined bending moment and axial load. The axial load is almost always compression, although there are rare cases of net tension on a column, in which case we call it a tension tie. Okay, and the P sub u and M sub u will both have to be less than or equal to phi times P sub n and phi times M sub n. Okay? It is as simple as that. Now, if it is a slender column, in one of the approaches that we use for the design of slender column, we magnify the moments that are actually applied by the loads, as you will see in later parts of this presentation. Yeah. So the load moment interaction diagram, this is the flexural strength M sub n. Okay, this axial load is typically denoted by P sub 0, that is the P sub n at zero eccentricity, when there is, at least theoretically, no moment. This is the this corresponds to balanced conditions. The axial load is P sub b, the bending moment is M sub b. Balanced, as always, means the steel reinforcement, the tensile steel reinforcement yields at the same time the concrete, the extreme concrete compression fiber gets to a strain of 003. Okay? So that's balanced condition. The eccentricities are denoted by those inclined lines. This is at any point, the eccentricity is the bending moment divided by axial load. The balanced eccentricity is the balanced bending moment divided by the balanced axial load. Okay? M sub b divided by P sub b. I don't know that figure tells you much more. Obviously, in this part of the interaction diagram, strength is controlled by yielding of the reinforcement. This is, if you like, tension control behavior, although it is much more precisely defined in the code. And in this part, above the balanced axial load, strength is controlled by crushing of the concrete rather than yielding of the reinforcement. Now, pure compression, when there is no bending moment, eccentricity is 0. The strain is uniform over the entire cross section. That's what pure compression would mean. Okay, we have 003 over the entire cross section, not just at the extreme compression fiber. There is now no extreme compression fiber. The column is uniformly compressed. The uniform strain is 003. No bending moment. Balanced strain conditions, the eccentricity is the balanced axial, the balanced moment strength divided by the balanced axial strength. Okay, we are talking about the nominal interaction diagram. Compressive strain in the concrete reaches 003 and the extreme tension steel reaches yielding. Okay, as that is definition of balanced condition. Pure flexure on the x-axis, the eccentricity is now infinity. the if there is no bending moment, then P over M, the eccentricity is obviously infinity. Compressive strain in the concrete reaches 003 after the extreme tension steel reaches yielding, after, because we have under reinforced beams, remember. So compressive strain in the concrete reaches 003 after the extreme tension steel reaches yielding. Compression control segment, that would be below the balance point. Eccentricity is below eccentricity at balance point. Compressive strain in the concrete reaches 003 before the extreme tension steel reaches yielding. So this is compression dominated behavior. The concrete controls the behavior. The transition or tension control segment, you don't go from compression control to tension control. Remember, compression control is net tensile strain of 002 or less. Tension control is net tensile strain of 005 or more. In between, there is a transition zone. So if we taken away the compression control part, then we are left with transition and tension control segment, where epsilon sub t is larger than or equal to 002. Eccentricity is larger than eccentricity at balanced strain condition. Also, compressive strain in the concrete reaches 003 after the extreme tension steel reaches yielding. So this is tension control behavior, or in the transition region, we are approaching tension control behavior. Okay. This, I don't know that we need to spend a lot of time. So when there is no eccentricity, theoretically at least, it's pure axial loading. This is your strain diagram, 003 across the entire section. Okay. When strength is controlled by crushing of concrete, that means the bending moment is large. The other way. Strength controlled by crushing of concrete will be when the axial load is high compared to bending moment. And then your strain diagrams look like this. The reinforcing steel, the tension steel, does not yield when the extreme compression fiber concrete strain is 003. And then tension control or transition sections, you have the reinforcing steel yielding before the compression concrete crushes. And that gives you tension control behavior. Okay. This is the only place I have brought in biaxial bending. This is from the commentary to ACI 31808. I gave you the section numbers 1036, 1037. Biaxial bending of columns tends to be a topic in itself, and I left. It seems to me that I left more things out than I included because, as I said, you can only cover so much in 2.5 hours. So how do I want to say it? Pre-stressed columns would have been a good topic. We have a session on pre-stressed concrete separate. This was the main reason I didn't include it here. how much coverage columns will get in that course, I do not exactly know. Then the seismic part, which is very important, seismic design of columns will be covered in detail in other segments. So here, topics like biaxial bending probably would have been logical if we had time, but anyway. So this is an expression that is given, as I said in the commentary, the P sub nx, let us start there, here, this thing. So P sub nx, nominal axial load strength at given eccentricity along x-axis. If you have eccentricity of the axial load only about the x-axis, the nominal strength of the column is P sub nx. If you have eccentricity of the axial load only about the y-axis, the nominal column strength is P sub ny. And if you have no eccentricity, it is a concentric axial load, then the axial load capacity is P0. Now, if the axial load is applied at an eccentricity with respect to the x-axis and an eccentricity with respect to the y-axis, it does not sit on either the x-axis or the y-axis. It has an eccentricity with respect to both. Okay? Then the nominal strength is P sub ni. And P sub ni is given in terms of the other three quantities by this expression. Okay, so as I pointed out, this is from the commentary to ACI 31808, sections 1036, 1037. There is a little more writing there than I have reproduced. So it will be, if this is your topic, it will be worth your while reading it. And there is quite a bit of literature actually going, I would say, back to Noel Everard and so forth. Those would be the 70s at least, that we have literature on biaxial bending of columns. Okay, design dimensions of compression members. Here, instead of reading a couple of things, if you have this kind of a column, I don't know how often you might have that. The effective cross-section can be taken as the one drawn in blue. Okay, so maybe after seeing that, outer limits of the effective cross-section of a compression member with two or more interlocking spirals shall be taken as at a distance outside the extreme limits of the spirals equal to the minimum concrete cover required by 7.7. Okay, so that is the minimum cover that the text was talking about. And the other situation, probably more common, we call them pilasters, a column-like element built as part of a wall. Then the column section is taken as shown in this particular picture. ACI 318 is very specific that part shall be designed as a column. Next item says something that I definitely have never done it. I don't think I have seen people do this, but anyhow, as an alternative to using the full gross area for design of a compression member with a square, octagonal, or other shaped cross-section, it shall be permitted to use a circular section with a diameter equal to the least lateral dimension of the actual shape. Gross area considered, required percentage of reinforcement, and design strength shall be based on
that circular section. As I said, I have no feel for how accurate or good this is. It is there. I thought I would bring it to your attention, but again, I personally have never gone there. For a compression member with a cross section large, this is extremely important, extremely important. Okay, so for a compression member with a cross section larger than required by considerations of loading, this is very common. I'll tell you why. It shall be permitted to base the minimum reinforcement and strength on a reduced effective area, not less than 1/2 the total area. This provision shall not apply. Okay. So again, the English when you read it is not the clearest. What it is saying is this. In a column, you cannot place reinforcement less than 1% of the gross cross-sectional area. 1% reinforcement is the minimum. Now, if you have more area than you need to carry loads, okay, to carry the loads that are coming on your column, you need 100 square inches. But for whatever reason, you have provided a column with a cross section of 200 square inches. Now you don't have to provide 1% of 200 square inches. You can provide 1% of 100 square inches, the area that is required to carry the loads, not the area that you have provided. However, you cannot go below half a percent of the area that you have provided. Okay. So if instead of 100 square inches, you had provided 300 square inches of area, your minimum reinforcement would be 1% of 150 square inches. Okay, are you with me? This is extremely important because let me tell you something. We never, basically never design a column. We design a column stack. If it is a 40-story building, we design a stack of columns that is 40 stories tall. Okay. Now, from story 1 to story 40, we are not going to change the cross section of the column 40 times as the axial decreases. That would be prohibitive. The formwork gets very complicated. I do not know if you realize formwork which does not stay in place beyond 3 or 4 weeks costs typically at least half the cost of a concrete structure. I don't mean the completed structure with glass and marble and bathrooms, no, but the structure itself, the skeleton before other things go in. The cost of the structure, half of that cost is in the formwork. So you have to keep formwork simple. So today, in most cities of the United States, they would design definitely 20-story columns, 30, sometimes even 40-story columns, column stacks, without any change in cross-section. As you go up, two things change. At the very base, where the loads are the highest, you use a very high compressive strength of the concrete. You may go with, I don't know, 11, 12 KSI. And a very high reinforcement percentage, something like 3 or even 4%. Then you taper the reinforcement off. As you go up and the load decreases, you decrease the reinforcement. By the time you have hit 1%, you switch to
a lower concrete strength and a higher reinforcement percentage. And then you do the same thing. You taper the reinforcement off, and when you have reached 1%, you switch to even a lower concrete strength. So at the very top of the building, we typically end up with 4,000 psi concrete and 0.5% reinforcement, not 1%, because the column in those parts will be much larger than needed for the loads. So we go with 0.5% reinforcement. Okay. Now this decrease of 1% to 0.5% is not allowed in a column that is part of the seismic force resisting system in a high seismic design category. Okay, so that is what the last thing is saying. Now this was 2008. These days we do not allow the 1% to go down to 0.5% even in a column that is not part of the seismic force resisting system if the building is in a high seismic design category. Okay, that part we will discuss when we go to the seismic modules, but very importantly, minimum reinforcement ratio is 1%, but for columns that are larger than needed for loads, we can go down to 0.5% reinforcement. Okay. The minimum and the maximum. Okay, and this I find very interesting. Okay, so minimum 1% I discussed already. Okay, it's actually 0.5%. Now 8% maximum. High seismic, it goes down to 6%. Now 8% reinforcement, if you ask me, it counts the laps. Typically, dowels will stick out of the foundation, and then you will lap the column bars with the dowels, and then the column will be cast and so forth. At the lap splices, the laps count. So 8% reinforcement is really cut down to 4%. Okay? Remember that. So 8% is not 8%, it is really 4%. And next thing I will say is even 4% reinforcement is way too much. But what I found interesting is in BNBC 2020, this is the added language in blue, BNBC says to avoid practical difficulties in placing and compacting of concrete, as well as to deliver ductility to non-composite compression members, area of longitudinal reinforcement is preferred not to exceed 4% of A sub G unless absolutely essential. This is such good advice. This is I was so glad to see it that the code says this. Okay, never ever go beyond 4%. The best columns are the columns with 1.5% reinforcement, something like that. They are ductile. They are good in every way. When you are pushing, going to 3-4% reinforcement, you are getting inferior structural members. You cram that much steel into a member, you are taking away from ductility. Also, reinforcement placement becomes a problem. Not so much the reinforcement placement, but placing the concrete after you place the reinforcement. Anyway, minimum number of bars, 4 bars when you have rectangular or circular ties, 3 bars with triangular ties, 6 for bars enclosed by spirals conforming to section such and such. This is a nice picture that I hope you will enjoy. So 8 number 20 or 1% reinforcement in the left-hand picture, 4% reinforcement in the middle picture, 8% in the right-hand side that has number 40 bars. Okay, now remember very importantly, we haven't discussed this yet. I hope to do it in that non-seismic detailing. These column bars have to be tied and cross-tied. Okay? There will be one tie all around, and then every other bar, this one and that one, has to be laterally supported by a corner of a tie or a cross tie. So there will be a cross tie around this bar, there will be a cross tie around that bar. However, if this bar is more than 6 inches from that bar, 6 inches clear, then there has to be a cross tie around those bars also. In that case, there will be 3 cross ties in each direction, plus the tie all around. So when you imagine the transverse reinforcement, the confining or the shear reinforcement together with these bars, you will see how difficult concrete placement becomes when you place too much reinforcement in a column section. So if you remember one thing out of this entire session on columns, it should be, do not cram too much reinforcement in your column. 3% is already high. 4% is way too much. Okay, the best columns again are the ones with 1.5% reinforcement. All columns cannot have that. Remember, you are designing column stack. Some columns will have more, but your aim is never to go to 4%. Okay, minimum reinforcement. Reinforcement is necessary to provide resistance to bending and to reduce the effect of creep and shrinkage of the concrete under sustained compressive stresses. So this is why we have minimum. The maximum reinforcement, this limit can be considered a practical maximum for reinforcement in terms of economy and requirements for placing. Okay, the spirals and the ties. Volumetric spiral reinforcement ratio, rho sub S. And I probably shouldn't try to explain that you should be aware of by now, shall be not less than the value given by the right-hand side. Okay? A sub G is the gross cross-sectional area. A sub CH is the poured concrete, that the area confined by the reinforcement. A sub CH has a very specific definition. Please look that up. I won't spend that time. So go to chapter 2 of ACI 31808. I don't remember without checking where the notation is in BNBC 2020. Look up the definition of A sub CH and please make sure that you use the exact definition. That definition has been moving around. This is why I don't want to give you something off the top of my head. I don't remember what it was in 2008. Okay? So anyway, so rho sub S, the volumetric spiral reinforcement ratio shall not be less than the value given by the expression, where F sub YT shall not exceed 700 MPa. That's 100 KSI. This is the place where we went to high strength reinforcement first. 100 KSI. This is already 2008. I believe we did that in 2002 or 5. I don't remember. For F sub YT greater than 420 MPa, lap splice according to such and such shall not be used. Okay, the spirals are lapped, and so what this is saying is that if you have those very high strength bars, then lap splice according to whatever section shall not be used. You have to do something else. Okay? You cannot lap. Okay, the amount of spiral reinforcement required by this that equation has been around if I remember correctly, that was developed at the University of Illinois in the I want to say in the 30s or 40s, that far back. This goes way back. Frank Richard, people like that. Anyway, and from then on, I mean, from the very beginning, the thinking was as is said in this commentary. The amount of spiral reinforcement required by the equation is intended to provide additional load carrying strength for concentrically loaded columns equal to or slightly greater than the strength lost when the shell falls off. So the idea is that when you compress on this column, spirally reinforced column, at one point the cover will fall off. You will lose the cover. That would amount to a decrease in load carrying capacity. But the confinement provided by the tight spirals will increase the concrete strength of the column inside the spiral. And this increase in strength should more than compensate for the loss of the concrete cover. That's the minimum amount of spiral was derived on that basis. Okay. Since 2005, the limit on yield strength, so it was done in 05, yield strength for spiral reinforcement was increased from 420 to 700 MPa. Okay. That's generally about columns. Then the pretty significant topic of slenderness effects in columns. Couple things. The way we deal with slender columns in ACI 318 has changed quite a bit from 31808 until 31819 today. So this is now, for me at least, going back to the way things were. That is fine, but I want you to know that. Secondly, the the much of it, not all of, like there are three ways of doing it: nonlinear second order analysis, linear second order analysis, and moment magnification. Moment magnification is the way it's not easy to do. There are too many provisions interlocking, too many things. So without examples, to get a hang of this is basically impossible. And I have absolutely no way of fitting in an example that would do you any good. So I would refer you to PCA's Notes on ACI 318. This is what the publication used to be called, Notes on ACI 318, published by the Portland Cement Association. 2008, the Notes on 31808 was the last one that was published in print. There apparently are notes on ACI 31811 that are available free of charge on the PCA. At one time it was on the PCA website. It still is, I do not know. And I do not believe there was a notes on 31814 even published. So that document has pretty much died because of things that have happened with the concrete industry in this country, which is a shame. But so that will be your best bet, and let us see when the there is, with the seminars going, there is absolutely no time. But at one point, I will take a look and see if there is an example that I can extract from that book and put on your portal so that you can make use of it. Okay. So without an example, I somehow feel a little bit uneasy. that this topic, you will follow at one level, but you will not get a real feel. That's what I'm afraid of. Anyway, so slenderness effects, section 1010 of the code. Slenderness effects shall be permitted to be neglected in the following cases. This is where we start, when you can forget about slenderness effects. Or compression members not braced against side sway. So these are sway members, as we call them, not braced against side sway. And what that means will be coming up. K L sub E over R less than or equal to 22. You can forget it. Okay. K is the effective length factor that we'll talk about. L sub U is the unsupported column height. R is the radius of gyration, which is square root of I over A, moment of inertia divided by the cross-sectional area. So K is the effective length factor, L sub U unsupported height, R radius of gyration. If it is not braced against side sway, then the limit is K L sub E over R less than or equal to 22. If it is a compression member braced against side sway, non-sway column, braced against side sway, then the limit is 34 minus 12 times m sub 1 over m sub 2. And this entire thing, 34 minus that, cannot be any larger than 40. How can this expression give you something larger than 40? Because this ratio is quite often negative. So we will get numbers more than 34. Okay. So compression members not braced against side sway on the previous page, braced against side sway on this page. KR, I have explained to you. Okay. So we have M sub 1 and M sub 2. It's extremely important that you get this part, what they are. M sub 1 is the smaller factored end moment. There are two ends, two moments acting. The smaller one is M sub 1. Okay, it's not top or bottom, this or that. The smaller moment is M sub 1. Smaller factored end moment on a compression member to be taken as positive if member is bent in single curvature. And M sub 1 will be taken as negative if the column bends in double curvature. Okay, so quite a bit is said there, and it is the smaller of the two end moments. M sub 2 then is the larger factored end moment on compression member if transverse loading occurs between supports, if there is a load, transverse load between the ends of a column, which is unusual. M sub 2 is taken as the largest moment occurring in the member, then it may not be the end moment. Value of M sub 2 is always positive. So M sub 1 is negative when the M sub 1 is negative when the column bends in double curvature, positive when it bends in single curvature. M sub 2 is always positive. Okay. And so if there is a horizontal load on a column, then bending moment may be maximum at a location other than an end, and then M sub 2 will be the largest moment, not the end moment. M sub 1 over M sub 2 is positive if the column is bent in single curvature. Obviously, M sub 2 is always positive. M sub 1 in that case is positive. However, if a column bends in double curvature, then M sub 1 is negative, M sub 2 is positive, so the ratio is negative. It shall be permitted to consider compression members braced. This is again very important. Okay? So braced versus unbraced, sway versus non-sway. It shall be permitted to consider compression members braced against side sway when bracing elements, typically shear walls in concrete buildings, have a total stiffness resisting lateral movement of that story of at least 12 times the gross stiffness of the columns within the story. Okay. So let us say you have to know the direction of analysis first of all. Okay. So when you design a column, there is an implied direction of analysis. The bending moments are bending moments that are being applied to the column assumes the building moving from left to right. Okay. When the building moves from front to back, there will be bending moment on the same column but in a perpendicular direction. Okay. We typically design buildings one at a time, so it doesn't necessarily have to be biaxial bending, but that's besides the point. My point is that there is an implied direction. So in the direction that you are considering, let us say you have in the story of which the column is a part, you have 6 shear walls running in the direction of analysis, and there are 36 columns. If the total stiffness of the 6 shear walls, okay, you know stiffness. If the total stiffness of the 6 shear walls is more than 12 times the total stiffness of the 36 columns, then you have a braced story. Okay, this number of 12 is in 31808. It used to be smaller before, and now I believe we have taken away the number. We have some language, but anyway, it's very good that you have a number in 31808. 12 is a very conservative number. You cannot go wrong. Okay, so it shall be permitted to consider compression members braced against side sway when bracing elements, read shear walls, have a total stiffness resisting lateral movement of that story of at least 12 times the gross stiffness of the column within the story. The direction part is not very clear in this writing, but anyway, so that kind of settles the issue of non-sway versus sway, braced versus unbraced. Okay, the unsupported length of a compression member, L sub U, shall be taken as the clear distance between floor slabs, clear distance. Beams, so that would be from the top of the floor to the underside of the beam, or other members capable of providing lateral support in the direction of direction being considered. So it doesn't have to be just slab or beam, any member that provides lateral support. Where column capitals or hunches are present, that column capital or hunch is a flared column top. L sub U shall be measured to the lower extremity of the capital or hunch in the plane considered. So lower extremity of the capital. Okay. The K factor, effective length factor. I thought it was good to go back to the basics. I took this, there are 2 pages of figures that I took from the textbook by Winton and Nilsson. I have over the years gone back to this page many times because it explains things in very basic, clear terms. Okay. So this is a column where the ends are restrained from translation. They cannot move laterally with respect to each other, but they are not restrained against rotation. And then K is equal to 1. Here, the ends are fixed, so there is no translation possible, and the rotation also is restrained. In that case, this portion between inflection points is similar to that. So K is 1/2. KL, the effective length, is 1/2 of the length of the column. Now, both cases I said there is no like translation is not possible. Okay, only rotation is possible in the first case. In the second case, rotation is also not possible. The translation not possible means there is no side sway. That's the language that is used. Braced against side sway, what we were discussing on the previous page. Okay. If it is a braced column, typically the ends will be neither fixed nor free. The column will frame into a beam or a slab at both ends, and the beam into which the column frames will provide some restraint that will be between this and that. The rotation will not be totally prevented. At the same time, it will not be totally free to rotate either. So K will be between 1 and 1/2, between these two cases. Okay. So case KL will be between 1L and 1/2 of L. Now we look at a cantilever column. Very obviously, the end can translate, if you like, and equally obviously, the K value is 2. The whole thing is like a column where the ends were not restrained against rotation. Now, when we have this situation, the end can translate but cannot rotate, then the K is equal to 1, as shown very clearly in the picture. Now, in a real case, this is the case of a sway column in a real life situation. So there is translation possible and rotation is partly restrained. Okay. So if the the best you can do in this situation is a K of 1. Okay. This situation, if the beams are rigid, then the rotation will be largely restrained. But since translation is possible, your K is going to be equal to 1. That is the best you can do in this situation. If this beam is flimsy and very flexible, then rotation is not restrained and translation is not restrained. And if that is true at both ends, both beams are flimsy, then we have an unstable situation and K is equal to infinity. Okay, so that gives you the whole range of K values. Now in SCI 318, even today, we have this, I forgot the name now, Jackson Moreland or something, these charts which enable you to calculate the K value depending upon the stiffness ratios at the two ends. Okay, the ratio of EI over L of compression members to EI over L of flexural members. So you will take the column stiffness to beam stiffness ratio at both ends, and depending upon the values, the psi A and psi B. So if your psi A is here, psi B is here, you draw a line between the two. Wherever you cross the middle line gives you your K value. I think most of you have done it. So this chart follows the principles that are described in the figure. So your K value, if you need it, you will very likely find from this chart that is in the commentary to ACI 31808. It is in BNBC as well, and you will need the column to beam stiffness ratios at the two ends in order to enter the chart. Okay, it shall be permitted to take the radius of gyration, KL over R, remember, equal to 0.3 times the overall dimension in the direction stability is being considered, or rectangular compression members, 0.3 times the dimension, and 1/4 times the diameter for circular compression members. For other shapes, it shall be permitted to compute R. R is simply square root of I over A based on gross section. Okay, what do you do when we say slenderness effect? How do you account for that in design? Where slenderness effects are not neglected as permitted by 10-10-1, remember KL over R less than 22 and so forth. If you cannot neglect them, the design of compression members, restraining beams, and other supporting members, so it's not just the compression members, but the beams that the compression members frame into and so forth, shall be based on the factored forces and moments from a second order analysis, satisfying. So there are three ways, as I said, 10-10-3, 10-10-4, 10-10-5. These members, so second order analysis that you can do in three different ways, if you like, 10-10-3, 10-10-4, 10-10-5. That's what those sections are about. These members shall also satisfy 10-10-2.1 and 10-10-2.2. We'll look at that. The dimensions of each member cross-section used in the analysis shall be within 10% of the dimensions of the members shown on the design drawings, or the analysis shall be repeated. So couple places something like that is said. So your analysis shall be done on columns that are on the design drawings. Okay, this is obviously important. Otherwise, you are not, you have gone someplace else. So the dimensions of each member cross-section used in the analysis shall be within 10% of the dimensions of the members shown on the design drawings, or the analysis shall be repeated. Okay, so 10-10-2-1, 10-10-2-2, there are two things that you have to satisfy for all slender columns. Total moment, including second order effects in compression members, restraining beams, other structural members, shall not exceed 1.4 times the moment due to first order effects. Okay, so total moment, including slenderness, cannot exceed 1.4 times the first order moments. That is a pretty important upper bound that has been agreed to by the committee. The concern is beyond that, if the moment including slenderness effects is more than 140% of the first order moment, there is potential instability, and we do not go there. Okay, so that limit has to be kept in mind. It's an important limit that again has been the subject of a lot of discussion subsequent to 3/1808, and I won't get there. So for you, that is definitely a given limit that you have to honor. And then second order effects shall be considered along the length of compression members, not just the ends, is the idea. Okay, it shall be permitted to account for these effects using the moment magnification procedure outlined in 10.10.6. Anyway, this also is in the notes examples that I was thinking of. It's not easy to do, but the requirement is that second order effects shall be considered along the length of compression members, not just at the ends. Shall be permitted to account for these effects using the moment magnification procedure outlined in 10.10.6. We will go there and you will see. Okay, so there are three ways of doing it. Remember 10.10.3, 10.10.4, 10.10.5. 10.10.3, this section is nonlinear second order analysis. Nonlinear second order analysis. Second order analysis shall consider material nonlinearity, member curvature and lateral drift, duration of loads, shrinkage and creep, and interaction with supporting foundations. The analysis procedure shall have been shown to result in prediction of strength in substantial agreement with the results of comprehensive tests of columns in statically indeterminate reinforced concrete structures. What is described here, everything has been thrown in. Material nonlinearity, member curvature, lateral drift, duration of loads. Anyway, the nonlinear second order analysis that this is asking for cannot be done. There may be research programs available here and there, I do not know, but to the practitioner, this is not a viable option. There is no computer program available on the market that will do this type of nonlinear second order analysis for you. So this is a theoretical option. You can just cross it out. 10.10.4, elastic second order analysis. This is not only not, how should I say, this is the opposite of the other one. This is more and more the way we do things. Okay, moment magnification, the other way. There has been serious discussion that we should throw it out. That hasn't happened, but most engineering offices will do this elastic second order analysis today in the United States. The elastic second order analysis shall consider section properties determined taking into account the influence of axial loads, the presence of cracked regions along the length of the member, and the effects of load duration. So this is sensible. So elastic second order analysis shall consider section properties determined taking into account the influence of axial loads, the presence of cracked regions along the length of the member, and the effects of load duration. Yeah, so very specific things, and those things can be taken into account. This is commentary. You don't have to do anything with it, but I think this is good commentary. Design computations for slender columns and frames and frames include both a strength reduction factor phi for the cross-sectional strength and a stiffness reduction factor phi sub k for the member stiffness. The variability in the cross-sectional strength is accounted for by phi in the interaction diagrams. You will see that in the interaction diagram, so we will go there. While the variability of member stiffness is accounted for by the phi sub k in the structural analysis. The phi sub k you do not see, but it is, that concept is kind of built into the numbers that we tend to use. Okay, stiffness is EI. The E part is modulus of elasticity of concrete as given in 851 of 318. So this is the expression. It includes the unit weight of the concrete. In your units, it's 2,400 kilograms per meter cubed. Here it says between 1440 and 2560. I guess that's the range of normal weight concrete. And a simplified version of that is this 4,700 square root of f sub c prime. This is for normal weight. Okay. So anyway, E sub c as given in ACI 318 BNBC 2020. The I, okay, most of the time you will use the I values given here. I would like to remind you that this is I think quite important. We are looking at section 1010 of the code, slender column design, and the I values given here are for that specific purpose, design of slender columns. However, we need stiffnesses for any structural analysis that we may want to do. And we always have to do structural analysis. Okay, we have wind acting on our building. We have earthquake forces acting on our building. How do we know the bending moment, shear forces in the structural members? By doing structural analysis. That requires stiffness assumptions. We have to assume the stiffnesses of the members. Since ACI 318 has never given us really the stiffnesses to assume for structural analysis purposes, it has some general provisions, nothing specific. Most engineers started using these values given in section 1010. And there are one or two places that are links between the two. I do not know that I will have occasion to discuss what I'm talking about in this lecture series. But in any case, what I'm trying to tell you is that ACI 318 basically never tells you to use these assumptions for general structural analysis. However, more and more that has kind of become practice. Okay. It is not code required. I want to absolutely emphasize that. Here, for slender column design, the code says it doesn't say you shall use these values, but you definitely are. The implication is that you will get the right results if you use these values. Okay, so I for compression members columns is 70% of I sub G. Walls, if they're cracked, 35% of I sub G, uncracked 70%. Beams or flexural members, 35% of I sub G. Flat plates and flat slabs, 1/4 of I sub G. That's kind of interesting. And area is 1.0 A sub G. We don't reduce. Okay, so most of the time for uh, this elastic second order analysis, which is what we are describing, we will take E sub C from ACI 318 or BNBC 2020. I values are as given here. Okay. So elastic second order analysis. Now, there are alternatives to these values given in the code. These are on the next 2 pages. We actually, these values come from 2 papers that one of my former employees and I put together many years ago. They're referenced. So this is our work. At the same time, I think you are better off with those simpler values. And I'm going to skip this more refined determination of I. That's what it's all about. Again, cross-sectional dimensions and reinforcement ratio used in the above formulas shall be within 10% of the dimensions and reinforcement ratio shown. This is talking about the formulas that we skipped, so let's not worry about that. Okay, now I don't know how important this is, but somehow 318 was pretty hung up about this for a while. Anyway, when sustained lateral loads are present, sustained lateral loads, that itself is pretty uncommon. Lateral loads are typically due to the 2 big ones are wind and earthquakes. Both are transient. They do not stay in place. They are not sustained. The sustained lateral load, the only one you can readily think of is earth pressure. If that exists, like the structure is retaining earth, and there is a difference in height between the earth retained by one face and the opposite face, then there is a differential in earth pressure that is acting on the building. That would be sustained. So anyway, when sustained lateral loads are present, I think the commentary says the unusual case of sustained lateral loads might exist. For example, if there were permanent lateral loads resulting from unequal earth pressures on 2 sides of the building. So this is admittedly an unusual case, but if you have that, then when sustained lateral loads are present, I for compression members shall be divided by 1 plus beta sub ds. This beta sub ds will be the ratio of maximum factored sustained shear within a story, maximum factored sustained shear within a story, to the maximum factored shear in that story associated with the same load combination, but shall not be taken greater than 1.0. Okay, I will probably leave it there. I think if you read that and just think a little bit, it will become clear. And I will, the more I talk, I think I will find the right example from the notes for you and post it. There is beta sub ds in at least one of the examples, as I recall. Okay, so that was 10-10-4. You do an elastic second order analysis, and the stiffnesses that you will use in that second order analysis are given. Okay. So the results of the analysis will reflect the slenderness effects. The Third way is moment magnification. This this is probably still quite popular in Bangladesh. I would assume it definitely has been in this country until I think it is now largely replaced by this second order analysis. This is my impression. Okay, moment magnification. The design of columns in non-sway frames or non-sway stories shall be based on 10-10-6. If it is non-sway, it is 10-10-6. Design of columns in sway frames is 10-10-7. I forgot about a break. Let's take 5 minutes here. I think we have been talking for a long time. So it's 41 after the hour. We'll come back at 46 and continue from here. Okay. So 5 minutes. Okay, let's start. We have quite a ways to go yet. So moment magnification, this is saying if it is a non-sway frame, then your section is 10-10-6. And if it is a sway frame, it is 10-10-7. Sway versus non-sway, we have discussed at least once. Shear walls having 12 times the stiffness of the columns in the same direction. Then it says it shall be permitted to assume a column in a structure is non-sway, the column is non-sway, if the increase in column end moments due to second order effects does not exceed 5% of the first order end moments. Okay, so take it for what it is worth. An individual column can be considered as braced, okay, non-sway, if the increase in moment due to second order effects is no more than 5% of the first order moment. It is also permitted to assume a story within a structure is non-sway if the stability index Q is less than or equal to 0.05. Okay. So that number again is 5%. The summation of P sub U is, well, summation of P sub U and P sub US are the total factor vertical load. Summation of P sub U are the vertical loads on all the columns in the story. P sub US is the story shear. Okay. The P sub U times delta sub 0 is secondary moment. V sub US times L sub C is primary moment. And this is the secondary to primary moment ratio and for the entire story. And that being less than 5% gives you a braced story. Delta sub 0 is the first order relative lateral displacement between the top and bottom of the story due to V sub US. L sub C is center to center column height. This is not the unsupported height. Okay, this is center to center of the floors. Anyway, so this is another way of approaching braced versus unbraced. This is 10-10-6. This is for non-sway columns or stories or whatever. Okay, non-sway situations. So the M sub 2, remember, is the larger of the two end moments. That magnified by a non-sway magnifier is your design moment, is your magnified moment. Okay? So M sub C is a non-sway magnifier multiplied by the larger of the two end moments. The non-sway magnifier is a C sub M divided by 1 minus P sub U, the factored axial load on the column, divided by 0.75, the critical load of the column. Critical load in Euler buckling, So the P sub C expression for that is pi squared EI over K L sub U squared. This is from strength of materials, if you like. So we magnify M sub 2 by a non-sway magnifier. Non-sway magnifier involves C sub M, P sub U, the column axial load, and the critical column load is P sub C. P sub C is pi squared EI over KL sub U squared. The EI that you use in this part in 10-10-6 is either this or that. Okay. 0.2 E sub C, I sub G plus, if you have reinforcement, the I of the reinforcement plus, then divided by the long-term factor, sustained load factor 1 plus beta DNS. This has a different definition now, as we will see. So you can use this when you have a lot of reinforcement, you will be better off using this, or you can use that where there is no reinforcement contribution. It's only 40% E sub G, I sub G, and then the long-term, the sustained load effect. Alternatively, EI can be permitted to, you can use the complicated formulas that I skipped, one of them, and divide by 1 plus beta sub ds. Anyway, the point is that the EI that you will use in calculating the Euler buckling load, the critical load, is given here, and there are two alternatives. The beta sub ds that is used in those stiffness equations is the ratio of maximum factored axial sustained load. We are talking about a column. It is the ratio of the maximum factored axial sustained load to maximum factored axial load associated with the same load combination. Again, if you think about it, you will see what it is saying. And again, I would tell you more importantly that beta sub sustained lateral loads are not common. Okay. What I just said, I take that back. Here it is not sustained lateral loads, it's any sustained load. Okay. So here you have to deal with beta sub s. The ratio of maximum factored axial sustained load to maximum factored axial load associated with the same load combination. Yeah. Without numbers, I cannot really explain any further, but I think that is understandable. The thing I shouldn't have done, this is not under sustained lateral load. This is sustained load, sustained axial load. Okay. The the effective length factor K shall be permitted to be taken as 1.0. Okay. So remember, these are braced columns, non-sway. So K is between 0.5 and 5, 0.5 and 1. If you go back to the basic picture that I borrowed from Winter and Nelson, if it is a braced column, K value cannot be any worse than 1. It is between 0.5 and 1. So you can always take K equal to 1 and be conservative. So that's what 10.10.6.3 is saying. And this is the commentary to that, which I'm going to skip. It says what I just said, that since it is a braced column, the worst you can do is a K of 1. Now the C sub M, remember the C sub M is a very important part of the determination of non-sway multiplier. C sub M is here. Okay? C sub M, P sub U, P sub C. The C sub M part is 0.6 plus 0.4 M sub 1 over M sub 2. M sub 1, remember, smaller of the end moments. M sub 2 is the larger of the end moments. M sub 1 over M sub 2, the ratio, once again, is positive if the column is bent in single curvature. It is negative if the column is bent in double curvature. That is going to be important. So if the column is bent in double curvature, this number will be small. If the column is bent in single curvature, this number will be larger. C sub M is 1 for members with transverse loads between supports, columns with horizontal loads between the ends. Those are uncommon, but it is not that they do not exist. This commentary, I will let you read it. It's kind of, I think that commentary confuses rather than adds clarity. Anyway, then in the case of compression members that are, this is also commentary, that are subjected to transverse loading between supports, it is possible that the maximum moment will occur at a section away from the end of the member. If this occurs, the value of the largest calculated moment occurring anywhere along the member should be used for the value of m sub 2, not the end moment, okay, the largest moment. And in that case, C sub m is equal to 1.0. Okay? Now this picture I also took from Winter and Nielsen, I took that in order to explain to you this difference between single curvature and double curvature, why C sub m is small for double curvature and larger for single curvature. So when you have end moments causing single curvature, as in this picture, okay, the end moments themselves give you this deflected shape and this bending moment diagram, and then the P, the axial load, because of the deflection, gives you additional deflections and additional bending moments. Are you with me? So the end moments themselves cause the dotted deflections and this bending moment. The axial load acting on the column because of the deflected shape will give you additional deflections as shown by the solid lines and additional bending moments given by the solid lines. And you can see that the moment is magnified quite a bit. Okay, it is quite a bit larger because of second order effects. Now in the second picture, the end moments are in you can say in the same direction. Here they're opposite, whatever. The end moments cause double curvature of the column. Okay, the end moments themselves cause the deflected shape shown by the dotted lines, and then the P delta effect adds to that and gives us this deflected shape. The bending moment caused by the end moments is now like this, and the bending moments caused by the P delta effects are like this. Now, the sum of this and that may look like this in the left-hand picture, or it may look like that in the right-hand picture. The point is that in this case, there is no moment magnification. The bending moment at the end is the same, and that is the largest bending moment. In this situation, the largest bending moment is no longer at the end, it has moved here, and the largest bending moment is larger than the end moment. So there is a little bit of moment magnification, but it is not anywhere near this. So when it is single curvature, moment magnification is significant. When it is double curvature, moment magnification is much less. And this is why C sub m is small when the column bends in double curvature, and it is larger when the column bends in single curvature. When bending in double curvature, anyway, I think I have made the point. Okay, now factored moment m sub 2 in equation such and such shall not be taken any less than. Okay, m sub 1 is the smaller of the end moments, m sub 2 is the larger of the end moments, m sub 2 shall not be taken any smaller than the value given. Okay, and then so the magnified moment will be this minimum moment multiplied by delta sub ns. for members in which m sub 2 minimum exceeds m sub 2, so the actual end moment is small, the value of c sub m shall either be taken equal to 1 or shall be based on the ratio of the computed end moments m sub 1 over m sub 2. In calculating c sub m, you will not use the minimum value of m sub 2. You will use the calculated value. Okay? So I think you will understand this if you just read. So the point is that there is a minimum end moment that 318 is imposing. Okay. Now we go to 10.7. This is sway columns or stories. Okay. So the m sub 1 now is m sub 1 non-sway plus m sub 1 sway multiplied by a sway multiplier. And m sub 2 likewise is m sub 2 non-sway plus delta sub s, a sway multiplier, times the sway moment. I want to read the definitions of, let us say, m sub 1 ns and m sub 1 s from 318 chapter 2, where the definitions are. I think it is worthwhile. It will take not a long time. Okay, so m sub 1 ns, this quantity. Okay, so I'm reading this. This is the meaning of the term: factored end moment on a compression member at the end at which m sub 1 acts due to loads that cause no appreciable side sway, calculated using a first order elastic frame analysis. Okay, read it again. Factored end moment on a compression member at the end at which m sub 1 acts due to loads that cause no appreciable side sway, calculated using a first order elastic frame analysis. This is m sub 1 ns. M sub 1 s, factored end moment on compression member at the end at which m sub 1 acts due to loads that cause appreciable side sway, calculated using a first order elastic frame analysis. So I think that gives you the best idea and explanation. Anyway, so loads that cause appreciable side sway, all lateral loads cause appreciable side sway, but if you have a and gravity loads typically do not cause appreciable side sway. There is an exception to that, however. If you have a very unsymmetric building, then gravity can cause appreciable side sway. So do not think always in terms of gravity versus lateral. Okay, so that's my advice. There are situations, not very common, but there are situations of a total lack of symmetry when gravity can cause appreciable side sway. Anyway, flexural members shall be designed for the total magnified end moment of the compression members at the joint. So this is not a trivial statement. If column end moment is magnified, the beam that the column is framing into also has to be designed for that magnified end moment. Otherwise, there is no equilibrium. Okay, so that statement is far from trivial. This I think I can skip, let you read. Okay, so the effective length factor K shall be determined using the value of E sub C and I given in 10.10.4 shall not be, now it shall not be any less than 1.0. Okay, so you can find your K from that chart. it obviously shall not be any less than 1.0. The SOI magnifier S is 1 over 1 minus Q, and it is larger than or equal to 1. Q was, remember, Q is very important, the secondary to primary moment ratio. I had it on, where was it? May have passed it. Yeah, somehow you have to go. Anyway, Q is in your hand. We just talked about Q not long ago. It's the secondary to primary moment ratio. Delta sub S is 1 divided by 1 minus Q. Obviously, it cannot be any smaller than 1. If delta sub S calculated by this equation, this is important, exceeds 1.5, delta sub S shall be calculated using second order elastic analysis. Then this moment magnifier approach is off. Okay, you cannot and should not use it. So if delta sub S calculated by this expression exceeds 1.5, delta sub S shall be calculated using second order elastic analysis. And you should at that stage abandon this moment magnifier approach. Okay, so this was for a single column, if you like. Alternatively, you can take a whole story. Delta sub S is 1 divided by 1 minus summation of P sub U on all the columns in the story divided by 0.75 times summation of the critical loads of all the columns in the story. Okay? So P sub C, K, yeah, those things we have gone over. If the lateral load deflection involve a significant, no, this I don't want to go into it. It brings in another complication that we don't need to consider. Now, in the calculation of EI, beta sub ds will normally be 0 for a sway frame because the lateral loads are generally of short duration. Okay? Sway deflections due to short-term loads such as wind or earthquake are a function of the short-term stiffness of the columns following a period of sustained gravity load. For this case, the definition of beta sub ds in 10.10.4.2 gives. So this is still, you know, this is sway frames, sway story, whatever. The deflections are being caused by lateral loads. So this beta sub ds now is again goes back to sustained lateral loads, and it is saying that sustained lateral loads are basically uncommon. Okay, so that is the end of slenderness discussion. Then under shear design of columns, I have summarized our discussion of a couple days ago. That's all there is. Shear design of columns, shear design of beams, really not any different. But our slide set was design of beams and one-way slabs for shear. So this is now design of columns for shear, done exactly the same way. I will skip the slides. Please check that there is no difference between beam shear design and column shear design. Okay. And then the development length part is the same. Development length splices I have summarized our discussion essentially from yesterday. Okay? Because that was, again, design of beams and one-way slabs, development length. Now this is development length, splices as they apply to columns. There is hardly any difference. So this is a summary of yesterday's discussion. Okay, only thing that I maybe will spend a few seconds on. So this is the, again, load moment interaction diagram. The P sub n is on the y-axis, typically M sub n on the x-axis. So in this portion, F sub s, the stress in the tension reinforcement is larger than 50% of F sub y. Between here and there, the steel, the stress in the tension steel is between 0 and 1/2 of F sub y. And here, all the bars are in compression. Now, this has implication for whether we can have type A splices or type B splices. So the example that I skipped yesterday and will do on Monday will relate to what this is talking about. Okay, I may or may not show this picture, but what this picture is about will come home to you when I do the last example in yesterday's slide set, which I skipped yesterday, but we'll do on Monday. Okay. So I will go on to today's example. Okay. So yeah, this example I think is a simple but a good one, and I'll make a few remarks after taking you through, and then whatever time is left will be for question and answer. Okay, so this is a column section 500 by 500. It's a square column. 4 number 32 bars, 2 at the bottom, 2 at the top. Bottom, top, or whatever. Yeah, 40 millimeter clear cover, number 12 ties, and this distance from the top to the center of the top bars is 68 millimeters. I skipped the the question. So construct axial load moment interaction diagram for the column section that you saw using 6 points. So figure out 6 points on the interaction diagram. Pure flexure, that's the x-axis. Item 2, when epsilon sub S1, that is the bottom reinforcement, that is layer 1. I think that's how we designate. Yeah, this is 1. So the strain in the bottom reinforcement is 005. Number 3, strain in the bottom reinforcement is equal to yield strain. Number 4, the strain in the bottom reinforcement is 1/2 of yield strain. And then number 5 is strain in the bottom reinforcement is 0. Okay, so 005 to this is 002, this is 001, this is 0. So strain in the tension steel is decreasing as we go. And then pure compression. Remember, 003 across the whole section. Concrete 40 MPa, steel for 420 MPa. Okay, the first item, we are on the x-axis. we want to calculate the, how was it phrased? Pure flexion. Okay. So Pmn is the moment strength. There is no simultaneous axial load. A sub S1 and A sub S2 are 1638 square millimeters, 2 number 32 bars. Assume the location of the neutral axis coincides with the upper steel layer. Okay. The location of the neutral axis coincides with the upper steel layer, meaning neutral axis depth is 68 millimeters. This is strictly an assumption. The section is under bending. Okay, no axial load. So C, we are assuming, this is just an assumption, is 68 millimeters. Beta sub 1 for 40 MPa concrete is 0.76. So stress block depth A is beta 1 times C, 76% of 68, which is 51.7 millimeters. D sub 1 is 500 millimeters total depth minus 40 millimeters of clear cover minus 12 millimeters of the, that's the tie diameter, and 1/2 of the 32 millimeter diameter of the bar. That comes to 432 millimeters. So the strain in the tension steel by straight line strain distribution comes to 0.16, which being larger than the yield strain, the tension reinforcement is yielding. So the stress in the bottom reinforcement is 420 MPa. The strain and stress in layer 2 are, obviously layer 2 is at the neutral axis, so there is no stress, there is no strain. The tension force is the area 1368 multiplied by the yield strength 688 kilonewtons. The compression force in the concrete 85% F sub C prime AB, 85% F sub C prime is 40, A calculated value 51.7. This is if we assume neutral axis depth is 68 millimeters and B is 500, so that gives us 879. C is not equal to T. Compression is not equal to tension. The section is not in equilibrium. Okay. Now we find that the compression concrete force is higher than the steel force, so the neutral axis depth needs to be shallower. So now we try a neutral axis depth smaller than 68 millimeters. By trial and error, we arrived at 61 millimeters. Neutral axis depth corresponding to that is 46.4 millimeters. Okay, so this is the strain diagram 003, 68 millimeters to the upper steel layer. That's the strain there is epsilon sub S2, strain at the bottom is epsilon sub S1, and D is 432 millimeters. Okay, epsilon sub 1, the strain in the bottom steel from straight line strain distribution comes to 0.18. So this steel is yielding and the stress is 420 MPa. The strain in the upper layer of reinforcement is 00031. That steel is definitely not, that steel is in tension. The neutral axis depth is shallower than 68, but it is small tension. It is definitely not yielding in tension. The stress in the upper layer of reinforcement is the strain of 00031 multiplied by the E sub S, the modulus of elasticity of the steel. That gives us 62 megapascal in the upper layer of reinforcement. So T sub 1 is 688 as before. T sub 2 is the area 1638 multiplied by the 62 MPa that we just calculated, that is another 102 kilonewtons. So this is a tension, that is a tension. The compression concrete force, 85% F sub C prime A B comes to 789 kilonewtons. The compression minus the two tensions is just 1 kilonewton, which is as good as 0. So we have found the right neutral axis depth and of 61 millimeters. Okay. Now we take moments of the three forces, the compression concrete force, the layer 1 tension, and the layer 2 tension. We take all the moments about the neutral axis. Okay. So this is the expression for the moment. The C sub C calculated value, C neutral axis depth is 61, A is 46.4. When we put all the numbers in, 285.8 kilonewton meters is M sub N, okay, nominal moment strength. Epsilon sub S1, extreme tension fiber strain, is 018 calculated value, that being larger than 005, we have a phi of 0.9. It's a tension control section, phi of 0.9. So the phi times M sub N, which is what we are after, is 257.2 kilonewton meters. Okay, no axial force to go with it. So that is part 1 of what we had to do. The second point corresponds to strain in the bottom layer of reinforcement equal to 005. Yeah, 005. So if we have 003 at the top, we have a strain diagram, 003 at the top, 005 at the bottom. Then the neutral axis depth by straight line strain distribution is 162 millimeters. This is the neutral axis depth, okay, from straight line strain distribution. The stress block depth is 76% of that, that's 123 millimeters. The strain and stress in layer 1 by straight line strain distribution, no, we don't even need that. The problem statement said the bottom layer of steel has a strain of 005, which is larger than the yield strain. So the stress in that steel is 420 MPa. In layer 2 by straight line strain distribution, the strain is 00174. This is a compression strain. The F sub S2 is that strain multiplied by the modulus of elasticity of the steel, that is 348 MPa. Okay, the upper layer of steel is now in compression. The neutral axis depth is here. So 348 MPa. So the tension is the 1638 is the area of the two bars. 420 is the yield strength. We have 688 kilonewtons of tension in the bottom bars. The compression steel force is the compression steel area multiplied by the stress, that comes to 570 kilonewtons. And the compression concrete force is 85% AB. We took out the compression steel area. This is typically not done. Theoretically, you should do it. Practically, we typically not do it. Anyway, that gives us 35 kilonewtons. So the P sub N is the two compressions minus the tension, and that is 1917 kilonewtons. Okay, So the axial force on the section, that would be P sub n, is the two compressions minus the tension. That is 1917 kilonewtons. And then we take moments about mid height of the section, 250 millimeters from the top or the bottom of the two compression forces and the tension force. That gives us a nominal moment strength of 612.6 kilonewton meters. Okay. The strain in the tension reinforcement of 005 still gives us a tension control section. Phi is 0.9. So phi times m sub n is 551 kilonewton meters. Phi times p sub n is 1725 kilonewton. So that is the second point on the interaction diagram. Third is when the bottom steel strain is equal to yield strain. So yield strain is 002, 0021, something like that. So by straight line strain distribution, neutral axis depth is 254 millimeters. The stress block depth is 193 millimeters. The stress block, the neutral axis depth is increasing from case 1 to case 2 to case 3. The strain in the tension steel is given as the yield strain 0021. So the tension steel is yielding, and the stress in that is 420 MPa. The strain and stress in layer 2, the upper layer of steel, the compression strain by straight line strain distribution is 0022. The two top bars are now yielding in compression. Okay, the neutral axis depth is deep enough that those two bars are yielding in compression. So the stress in the top bars is also 420 MPa, but this is compression. So the tension force is the area of the tension steel times yield strength, 688 kilonewtons. The compression in the two upper bars is the same. It is compression, but it is the total area times the yield strength, 688. So the two, the upper and lower layers cancel each other. There is no force contributed by them. Yeah. The compression force in the concrete for the calculated neutral axis depth comes out to 3225 kilonewtons. So 3225 is the P sub n value. Okay, the compression concrete force is now the P sub n. M sub n, by taking moments of the three forces about mid height of the section, the M sub n comes to 745 kilonewton meters. Epsilon sub S1 now is 0021. Okay, 002. So this is the beginning of compression control. And since this is a tied member, the phi is 0.65. So the 745 kilonewton meters of moment goes down to 484 kilonewton meters, that is P times M sub n. And the 3225 kilonewtons of axial force goes down to 2096 kilonewtons, that is the P times P sub n. Okay. Point 4, the strain in the tension steel is half of the yield strain. Okay, half the yield strain. This is now 001 or something like that. Okay, so the neutral axis depth comes to 001, half the yield strain. Neutral axis depth comes to 324 millimeters. It has increased even further. The depth of the stress block is 246, 76% of 324. For this strain 001, F sub S, the stress in the tension steel, the bottom steel rather, is 1/2 of the yield strength. The strain is 1/2 of the yield strain, so the stress is 1/2 of the yield strength, and that is 210 MPa. The strain in the upper layer by straight line strain distribution is 0023. This layer is definitely yielding in compression. So the stress in this layer is 420 MPa. This is tension, that is compression. The compression concrete, so tension steel force, the compression steel force, the compression concrete force for the calculated value of A, 4126 kilonewton. So the axial load, P sub n is the two compressions minus the tension, and that comes to 4470 kilonewtons. And then by taking moments of the three forces about mid height of the section, the moment strength comes to 712 kilonewton meters. This section is still definitely compression controlled. The net tensile strain is 001. So P times M sub n is 463. Phi times M sub n is 2906. Finally, the case of pure compression, there is no strain in the no tensile strain in the bottom reinforcement. No, this is not that. No, this is not pure compression. This is where the strain in the bottom reinforcement is equal to 0. Okay, so the depth of neutral axis is the depth to the bottom reinforcement, which is 432 millimeters. So no strain in the bottom reinforcement, which means neutral axis depth is the distance from the top to the center of the bottom reinforcement, and that is 432 millimeters. The stress block depth that corresponds to that is 328 millimeters. Okay, this is the strain diagram, no strain in the bottom steel. So layer 1, the bottom layer, no strain. The upper layer, which is in compression, the strain is in excess of the yield strain, so the upper layer definitely yields. 420 MPa is the strength. There is no tension force. The compression force in the upper two bars, 688, because they're yielding. The compression concrete force is very high, 5520, because most of the section is in compression. So P sub n now grows to 6208 kilonewtons. And then by taking moment of now there are two forces about the mid height of the section. The moment is 600 kilonewton meters. Phi remains at 0.65. So those are the design values of moment strength and axial strength. And the pure compression, the final number, P sub n is given by that expression. 85% of F sub C prime multiplying the concrete area and F sub y multiplying the steel area. That gives us 9765 kilonewtons. Okay, so if we want a phi, the phi is 0.65. So the P times P sub n is 5078 kilonewtons, and there is no moment to go with it. Okay, So that will give us, so we calculated nominal values, we calculated design values, so we can plot this diagram on that. So the first point was here. How did we put it? Like no uh, axial load, however. So first was here. And then the second point was, as I recall, the strain in the bottom steel was 005. And then the strain in the bottom steel was 002, would be someplace here. Then it was 001, and then it was, I think, 0, and then we went all the way up to here. I don't know, something like that. So these very important load moment interaction diagrams are constructed using computer programs that are available. Almost nobody will do it by hand, but the exercise that we went through, I think, is extremely valuable. You see the neutral axis depth shifting. You see how the numbers are changing. If I had more time, I would probably stress the how the axial loads and moments are changing. Okay, very nice to see. And then the last thing that I would say is about column design. Okay, so when we design a column, looking at the loads and a whole lot of other things, like, remember, we design a column stack, not a column. And we do not design one column stack, we design many column stacks. So looking at all of that, we will come up with a column size, and then we will try out an amount of reinforcement based on the loads, and that is easy to do. To find a value to try is very easy to do. And then we construct for the section that we have come up with the load moment interaction diagram. This is the nominal diagram, this is the design diagram. And then we plot all the combinations of P sub u and M sub u that we are designing for, coming from the different load combinations. If all the points are within the design diagram, then our section is good enough for our purposes. Now, if all the points are clustered here, all the demands of P sub u and M sub u are clustered here, and this is my design interaction diagram, that tells me that I have overdone it. So that would be a good basis for reducing the reinforcement. You will typically not touch the column section because of other considerations, but you will reduce the reinforcement. These days, you can also play with the concrete strength if you like, and see if you can make the design less conservative. Anyway, so that is column design. You try something, you draw the load moment interaction diagram, you see where your demands fall. When I say demand, it is P sub u, M sub u combination coming from different load combinations. Okay, those are the demands. And if the demands are within supply, you are fine. If the demands are way smaller than the supply, then you may want to polish your design, make it a little less conservative. Okay, thank you very much. This is about what I planned for today. So now I'm open for questions, and we will do it the same way. Both you will read to me, and if I can answer, I will answer. Okay.
Thank you, Dr. Ghosh. Okay. So which one is recommended in circular column for high seismic zone, spiral or circular ties?
Spiral gives you better behavior than circular ties for sure. Which one is recommended? I do not know. That depends essentially on pricing. Yeah, I do not know.
Okay. So I'm just trying to
Sure.
check the questions that are relevant.
Mm-hmm.
Okay, let me try to frame this question. If a structural crack develops in a ground floor concrete column and concrete spalling occurs,
Mm.
how can we calculate its present capacity? Should we ignore the cracked portion concrete and rebar during calculation? I didn't understand.
So the column has cracked and has spalled.
Yeah.
How can we calculate the capacity? Yeah, I do not know a direct answer, but if a column has cracked, a column is under compression almost always. If a column has cracked, there is a problem. So it has been subject to tension for some reason. I would rather figure out what happened than try to figure out the capacity that may remain. So spalling indicates high compression.
I think resting also leads to spalling.
Well, yeah, rusting does lead to spalling. Rusting can cause, yeah, but if there is a horizontal crack in a column, that is not caused by rusting. That has deeper and bigger problems. So if it is only spalling, it is one matter. If there is really a horizontal crack in your column, you better figure out what is going on. I wouldn't seek to uh, calculate remaining column capacity. Remaining column capacity would make sense if there is just spalling. You probably will forget about the covered concrete, and I don't know. Theoretically, you should figure out the strength of the reinforcement in place by taking some coupons or something. So I do not know the basis of your question, why you need this capacity, and how you will calculate it will depend on the purpose of the calculation. What purpose you need this strength for? Okay.
Okay,
But
so this thing you answered already, but maybe you can address it more further.
yeah.
So if we use a 12-inch by 12-inch column for a certain load and
Mm,
use four 16 mm dia bar, but the
mm.
spacing between longitudinal bar is more than 6 inches, is it okay?
Read that one more time.
If we use 12-inch by 12-inch column for a
Mm.
certain load and use four 16 mm dia bar, but spacing between longitudinal bars is more than 6 inches, will that be fine?
Yeah, that's totally fine. What the 6 inches is if there are two bars more than 6 inches apart, then you need the bar that is more than 6 inches apart, laterally supported by a corner of a tie or a cross tie. Here you have four bars. All four bars are laterally supported by a corner of your tie, and you are fine. So 12-inch by 12-inch column with four bars, obviously the spacing between the bars is way more than 6 inches, and there is absolutely nothing wrong with that.
Yeah. Okay.
Now let me continue a little bit. Let us say in that column, 12-inch by 12-inch column, instead of 4 bars, you had 6 bars. Okay, so there are 2 additional bars, and somehow you place the additional bar not in the middle. If it were in the middle, you wouldn't go beyond the 6-inch clear spacing. But let us say you place the additional bar 8 inches from the corner bar. Then you have more than 6 inches of clear spacing between this bar and the corner bar. Now these additional bars will require a cross tie. Okay, so that's how it works.
You already discussed this. That's what I was saying. That
Yeah.
we can go to
Every other
executive
bar has to be laterally supported, and if you have more than 6-inch clear spacing, then additional lateral support may be needed.
So for a column splice, do we consider tension or compression development length? If we use development length of 10 for tension, then do we use tension top bar or bottom bar? I didn't understand.
Yeah, no, I understand. The first question is it tension splice? It is compression splice. Okay. You can use compression splice in a column only if you are sure that there will be no tension in your column bar that you are splicing under any of the load combinations that you are considering in design. Okay, so please listen to me carefully. If there is going to be tension in your bar under any of the load combinations that you are considering in your design, then you better use a tension lap splice, not a compression splice on that bar. That is number one. Okay. The second thing, top bar versus other than top bar. Top bar versus other than top bar is for horizontal members, not for vertical members. Okay. People have used it in walls and things. I personally do not believe that it is meant to apply to vertical bars in walls or columns. So don't worry about top bar effect when you are splicing column bars. Okay? That simply does not apply. Okay, next.
Yeah. Why usually spiral reinforcement not used in circular columns? Is it prohibited?
So that again, what kind of reinforcement?
Spiral reinforcement
Yeah.
not used in circular columns.
No, it is used.
Yeah, that's what you said. I don't think you said that.
Absolutely. Yeah. No, what I said is spirals are used basically only in circular columns. It is not that you will never use spirals in a square column, but it is very, very seldom. The spirals are almost invariably used in circular columns. Okay. But I said that the circular columns themselves are relatively rare in buildings other than parking structures. So we don't have a lot of spiral usage in buildings other than parking structures. That's what I was trying to say anyway. So yeah, no, you got it totally opposite. No,
Yeah, he might have.
spirals are used in circular columns. Yeah.
Okay, just going through the. Yeah, this has been answered. Sure. There are a lot of questions related to attendance and quiz. I would request you to send those questions to support at Happy Portal. Like I have really stressed this topic a lot in the last previous webinars as well. Uh, okay, so if I have a column in which reinforcement requirement at ground floor is 10-inch square and 12-inch square at first floor column, should I continue 12-inch square from ground floor, or I can provide 10-inch square at ground floor and add extra reinforcement at first floor?
No, read that one more time.
If I have a column in which reinforcement requirement at ground floor column is 10-inch square and 12-inch square at first floor column, should I continue 12-inch square from ground floor, or I can provide 10-inch square at ground floor and add extra reinforcement at first floor?
I see. my question in my mind is, why would that happen?
Yeah,
Why would the
so
reinforcement decrease? I don't know. I
it
cannot.
is, yeah. Usually it's at that, it is the opposite.
Yeah, I can't quite think. But if that is so, there is no nothing to force you to continue the 12 inches down. You are totally free to add reinforcement. So there is nothing that tells you that reinforcement cannot be lower as you go down the building. It typically isn't, but for instance, if you increase the column section, then the reinforcement can decrease, and there is nothing against that. Maybe that's your case. Maybe you have a slightly larger section at the lowest level. I don't know. But yeah, no, there is nothing against it.
Yeah, yeah. Okay, there's one more question similar to this. I don't think if it is the same person, no, but a very similar question. Yeah, but you have already answered that. Can you discuss about the capacity calculation of circular column, which is tension governed? That is that E is eccentricity is greater than the EB for columns. For this type of column, which spiral or circular for this type of column, is spiral tie more effective than circular tie? Which of them is more effective? Yeah.
Yeah, I don't know what a spiral is definitely more effective. If by effective you mean how well it confines the concrete. The pitch of the spiral is typically closer than the kind of tie spacing we use for circular ties, and that also obviously increases the effectiveness. So what I want to say is that it is seldom that we compare. It is seldom that a spiral is compared with comparable circular ties. You know, if you have a spiral with a pitch of 3 inches, I doubt that if somebody wants to do the same column with circular ties, he will use 3-inch spacing of the circular ties. That typically is not done. In any case, even at the same spacing, the spiral would be more effective. It's continuous. The continuity itself helps in making it more effective, and this is why we give spirally reinforced columns a little bit of a better phi value than tight columns.
Yeah. Um, Sometimes it is very difficult to maintain hoop requirement in beam column joint due to huge rebar congestion. What do you suggest doing in such cases?
What I suggest is, as I suggested the other day, you draw the joint to scale at the design office, and if you find that bars don't fit, or after you put the bars in, concrete doesn't go in, then change something in the design. You cannot just set bars, bend bars or set bars aside, or drop bars. You cannot do those things. If the design requires bars to be placed at the joint, bars must be placed at the joint. If bars cannot be placed, then you better change your design so that so many bars do not have to be placed in the joint. Okay. The other measures that are taken, pea gravel and super plasticizer and all of that, cost a lot of money, and they should not be required if the joint is properly designed. And the best way to relieve congestion in the joint is deeper beams. Okay, if most architects will not quarrel with that, so there are ways of reducing congestion in the joint, and that's what you should be looking for. If there is a problem, you shouldn't try to solve it. What I'm trying to say is the problem should be solved at the design office, not at the job site. By the time you are at the job site, it is too late.
Yeah, a few questions are about software. Probably we can skip those. Should we insert column ties inside mat pile cap of shallow foundation?
Should we?
Insert column ties inside mat pile cap of shallow foundation.
Well, it is sometimes required, not all the time, but if you have in seismic situation, which is much of Dhaka, you have a column supporting a discontinued shear wall. The column cage has to continue at least 12 inches into the support. So there are cases where you are required to continue the column ties into the foundation, and even when not required, it is not a bad idea to do that. You don't have to go too deep, but yeah, something like 12 inches is a good idea. Sometimes it is 12 inches or one development length of the largest longitudinal bar, however much that is. So in the seismic area, there are specific requirements. Non-seismic, there is no particular requirement. But, depending upon what you are building, it may not be a bad idea to continue it for a little bit.
Okay. There are a lot of questions, Dr. Ghosh, and most of them have been answered by you. I don't know, they are asking for more clarification, maybe, or something like that.
Hmm.
And it's way past time right now. Like it's already 11 o'clock. So do you want to take one or two more, or?
Yeah, one or two more are fine. Yeah.
Okay, so 3 questions are related to this. How could we provide ties in circular columns? Can you tell us some details about that?
Circular columns will provide circular ties. It's as simple as that. You will not try to put rectangular ties in a circular column. Does not. There is no prohibition, but does not make any sense.
And few questions were related to like what is the minimum reinforcement rebar requirements for pedestal?
Pedestal, I don't know without looking. I, I typically don't do those. So, but it's in 318.
Yeah, yeah, yeah. So and the last question that we will take is if one column is a composite column and at the center there is steel eye joist,
Mhm.
whereas others are RCC columns, is it allowed for a high-rise building?
Mhm. Is it allowed for a high-rise building?
Yeah,
Is that the question?
that's the question. Like, if such an arrangement is allowed or not. Like,
Uh, the only problem I see, I don't know that there is a prohibition, but something should be checked out. Like if there is a steel shape in a column, uh, as I mentioned earlier, there will be redistribution of forces between the concrete and the steel, and the basically what I'm trying to say is that the shortening of this column, the composite column, may be different from the shortening of the other columns, particularly after a number of years. The time dependent part will be different, and that may cause problems. That may, you know, that may have an effect on the floor members that frame into those columns. This should be checked out. There is no prohibition. This is something that you can run numbers on, but this is something I would like to check out before proceeding with something like this. It's a problem of possible differential shortening. That's what we call it, differential shortening, particularly in the long run.
yeah. So I think we should end the webinar today, Dr. Ghosh. It's already
Okay.
past 11.
Okay.
Yeah.
Thank you.
Yeah. So we will have the next two sessions are on steel again, right? And that too over the weekend.
Saturday, Sunday. Yeah.
Saturday and Sunday. Yeah, right.
Yeah. Yeah.
Right.
And then Monday we will do two-way slabs,
Right.
Monday and Tuesday. Yeah.
Mhm.
Okay.
Okay.
Thanks very
Yeah.
much, buddy. Thanks very much, everybody. See you on Monday then.